Hi everybody. Today we're going to talk about section 8.2, which is about surface area of a surface of revolution. And we're going to build this by using the theory of arc length that we established in section 8.1. So the basic unit of our calculus intuition this time is going to be the lateral area of a cone. By lateral area, I mean the area on the outside of the cone here, not the cap, because we don't include the cap when we're talking about surface area. Okay? And you can also think, what is lateral area? It's the amount of paint that would need to be required to coat the outside surface of this cone. The way that we build out formulas for computing with a cone is we cut it and roll it out flat. So if I did that, I would end up with something like this, where I'd have some central angle theta in here that measured sort of something about how wide the cone was. And then this side would be L, because that corresponds to this L over here. And then this arc on the outside, well, that corresponds to the circumference of this circle. If you want a visual metaphor for this, you can think of taking the wrapping off the outside of an ice cream cone and splitting it down the seam and laying it out flat. This is the shape you would get. So I know that this on the outside is the circumference, which is equal to 2 pi r from the original cone over here in this case. This is a special type of shape called a sector of a circle. So this is called a sector. And we have formulas that relate the quantities, the arc on the outside, the central angle, and the radius of the sector out here. In particular, what we know is this. We know that the area of this sector is equal to theta, which is the central angle, times pi L squared over 2 pi. And you might think, well, where does that formula come from? The theta over 2 pi measures the portion of an entire circle that we're dealing with. And the pi L squared is the area of the whole circle that has L as a radius. We have another formula that relates theta to the circumference out here. And that formula is that this length on the outside is also equal to theta L. That the length of the arc on the outside of a sector is equal to the central angle times the radius of the sector. And what we can do is we can combine this formula with this one, and we can cancel the thetas out. So what we're going to try to do is we're going to try to combine this formula and this one in a way that will let us get the theta out of here. So I'm going to solve this for theta, which will give me an expression in R and L, and then I'm going to substitute in here, which should eliminate the thetas. If I set theta L equal to 2 pi r, then that gives me that theta is equal to 2 pi r over L. And that means that the area of the sector we were looking at is 2 pi r over L times pi L squared over 2 pi. The 2 pi's cancel, the L's cancel, or at least one of the L's cancels, and the formula you end up with is pi RL. So this is the basic expression for the surface area of a cone of radius r and slant height L. Let's bring this together. We have a cone. It has slant height L. It has radius r. And we know that the surface area, or the lateral surface area of this cone, is pi RL. So the basic idea that we're going to do is to cut surfaces of revolution into bands. And that means that we're going to think about not whole cones, but pieces of cones. We're going to model some sort of curved band as a chunk of a cone. And that's a special kind of object called a frustrum. Now, with a frustrum, we actually have two different radii to deal with. And we think of a frustrum, which is just, remember, a chunk of a cone, as having its own slant height, but also a slant height related to the original cone that it came from. So I'm going to call this L, and I'm going to call this L1. And then the radius of the upper circle I'll call R1, and the radius of the lower circle I'll call R2. And it's very easy to write down what the area of this should be, because I know areas for the big cone, and I know an area for the small cone, so you should just be able to subtract to get the surface area of the frustrum. So the surface area should be equal to the surface area of the big cone minus the surface area of the small cone, which is equal to pi times the big radius at the bottom, because remember we're dealing with the big cone right now, times the total slant height of that cone, which is right here. So that's L plus L1, minus the surface area of the small cone, which has radius r1 and slant height L1. Pi r1 L1. And you can take this expression, you can rearrange it so that it looks like pi times L1 times R2 minus R1 plus pi R2 L. And so now what our game is going to be to try to reduce this in as simple a way as possible. I'd like some sort of measurement where I can collapse all this stuff together. So after using our cone formulas, we've ended up with this expression for the surface area of a frustrum. And the problem from a calculus standpoint is that there's too many variables running around in here. What I'd like to do eventually is to collapse the height of the frustrum down and just have a single radius, but I've got two different radii in here. I've got R2 and R1. So now what I want to do is come up with some way of reducing the number of variables inside this. And the way that you can do that is you can notice that in the middle of the frustrum and its related cone, you have this set of similar triangles, R1, R2, L1, and L, and you can build a set of proportions using similar triangles that look like L1 over R1 is equal to L1 plus L over R2. So using that standard similar triangles type of setup, I get this proportion. If I cross multiply, I get L1 R2 is equal to L1 plus L R1. Now rearranging this formula, we're going to get L1 R2 minus R1 is equal to L R1. So what I did here was I multiplied through and I pulled over everything with an L1 onto this side. And the reason I did that is because this is an L1 R2 minus R1. And so I can replace all of this with this. And what that's going to give me is a new expression for the surface area that's simplified that looks like pi L R1 plus pi L R2. And that's equal to pi L R1 plus R2. And that means that I can rewrite this with an average of the radii of R1 and R2 by writing pi L R1 plus R2 over 2 times 2. After all, I can't just divide by 2. I've got to put a new 2 in. And ultimately what that means after all this derivation is that when I have a frustrum of a cone, and I have a radius 1 up here, and a radius 2 of the circle on the bottom, I call this slant height L, that the formula I get for the surface area is equal to 2 pi RL, where R is equal to R1 plus R2 over 2. So it's the average of the two radii. And this formula is our basic thing that we're going to be using to calculate the surface area of frustrums. And frustrums are the object that we're going to be using to approximate curved surfaces. So let's see how that works. Now suppose that we have a surface of revolution. So we take some curve and we rotate it, say, around the x-axis. And what we're going to end up with is a shape that looks like this. So we rotate around. This same curve appears on the bottom down here. And we have an opening up here that looks like this. So this is what a typical surface of revolution looks like. If I want to compute the surface area of the surface of revolution, what I could do is approximate it with a bunch of band pieces. And what I mean by that is, if I took a band of this, I get a piece that looks pretty similar to a frustrum. After all, this thing is almost like a chunk of a cone where we replace these little curved pieces on the side with little straight pieces. So what we could say is, oh, well, I'm not going to think of the band. I'm going to think of the cone piece that looks an awful lot like it, which means instead of thinking of this as a curved blue piece, I think of it as a straight piece. And down here, I replace this with a straight piece. And I can keep sort of the same endpoints, but that red frustrum approximates the blue band. So I'm going to cut the surface of revolution up into these bands, and each one of those bands I'm going to think of as being like a frustrum, and then I can use the surface area formula to figure out what the surface area of each individual band is. Now that's going to require that I know how long each one of these pieces is, because remember, the frustrum formula has a slant height in it. Well, the slant height is ds. It's the arc length from the previous section. So if you had a band that looked like this, and you replaced it with a frustrum, then what we're saying is that the frustrum has slant height L equal to ds, because we're approximating this curved piece with a little straight line segment. And so it can't be delta x because it's not a straight line delta x, right? As delta x goes over, we have to approximate what the length of that little curve part is, and that's our ds approximation from the arc length section. If this is really skinny, then the radius is going to be very close to the average of this side and this side. So we're going to say that r is equal to f of xi star for some xi star between xi and xi plus 1. So somewhere in the middle here is this radius, this average radius. So we think of this height right here as being r is equal to f of xi star, because we're just going up to this function. Remember, this comes from the function. That's actually enough information to write down an approximation for the surface area of the frustrum. So the surface area of the frustrum is 2 pi rl. What's the radius? Well, the radius was f of xi star. That is some function height inside this band between xi and xi plus 1. And what was the slant height for that cone? Well, the slant height is really the arc length of this blue part right here, which we're approximating with ds. And that means that we can write this as 2 pi f of xi star times the square root of 1 plus f prime of xi star squared delta x. So this nasty looking chunk right here is a very simple geometric derivation of the surface area that approximates this band. Okay. So if I'm going to rewrite this neater, 2 pi f of xi star, the square root of 1 plus f prime of xi star squared delta x. So that thing is the approximation for each one of these bands. If I had a whole shape and I wanted to approximate its entire surface area, I think of taking this and cutting it up into lots of bands. The ith surface area is going to be about equal to 2 pi f of xi star square root of 1 plus f prime of xi star squared delta x. Remember, all that we really did here was, this is really the formula 2 pi rl. So if I want an expression for the area of the entire thing, I have to add all of these up. So the surface area for the whole object here is about equal to the sum from I equals 1 to n of 2 pi f xi star square root of 1 plus f prime of xi star squared delta x. And if I want this to be accurate, if I want this to accurately approximate the surface area instead of using banded approximations, I need to let the number of bands go to infinity. So if I take the limit as n goes to infinity of the sum from I equals 1 to n of 2 pi f of xi star square root of 1 plus f prime of xi star squared delta x, that is the surface area of each of the bands added up, but I let the number of bands go to infinity, you end up with what's called the surface area integral. The integral from a to b of 2 pi f of x times the square root of 1 plus f prime of x squared dx. This is the surface area integral. This frequently is solvable in cases where the arc length isn't, because a lot of times you get substitutions here. The fact that you have this extra bit floating around in the outside of the integral sometimes allows us to come up with integrals that can be solved in an easier way with u substitution, say. It's still important to recognize that many of these integrals are not solvable without using numerical approximations, but having an expression for the surface area by itself is very important. So frequently our task as mathematicians, physicists, or engineers is to construct the formula, and then the computer does the approximation of the integral formula, even if we can't solve it. I should also point out that there's a corresponding y formula for when you rotate around the y-axis, and that is given by surface area is equal to the integral from c to d of 2 pi g of y times the square root of 1 plus g prime of y squared dy. And frequently what mathematicians like to do with these formulas is condense them using ds to represent all these nasty square root pieces. The square root pieces don't change. From the last section, we knew that these things were unit arc length. And so to make these formulas smaller, what you could do is write that surface area is equal to the integral from a to b of 2 pi f of x ds in the case where you're rotating around the x-axis, and that it's equal to the integral from c to d of 2 pi g of y ds when you're rotating around this.